You should be good.
Okay. Wait, it's not displaying them though.
Let's say HDMI 1.
Cool. All right. Okay. Hello. I'm Aiden, and this is Max, and we're doing a presentation on 3D printing. So, it's basically about like the applications, general applications of 3D printing, and what we use it on our team specifically. Bro, why is it not working?
Wait, Sam, it's not connected. Huh?
Okay. Oh wait, it's just displaying.
Alright, so yeah, first of all, what is 3D printing, right? So it's pretty self-explanatory, printing in 3D. So first, I guess there's the whole process to it. You gotta have a digital file first, and most of the time you need a 3D model for that. And for our purposes, we have CAD models, and to do that, you first have to transfer a CAD file into a STL file, which is what most 3D printers use. And then from there, you can basically and we'll explain it later on, but you can basically take the STL file and change it into a 3D structure, and the printer will just print it layer by layer, kind of like what you print with a piece of paper, except it's just 3D, yeah. And like printers, there's a whole printing, it isn't instant. You have a whole process for that, and it takes a while for the print to be finished, and that just depends on how big your model is and how detailed you want it to be.
Yeah, so why should you 3D print? So first is it's really convenient for prototyping. It's really cheap and it's fast, especially on things like smaller 3D printers like the Ultimakers. You can model things really fast. And specifically for things that we use it for, so most notably custom structural components, like our shooter hood on Excelsior, which is our competition robot for 2022. It's a big 3D printed part that we printed on the Stratus. Other things that other structural components are like bearing blocks, where you put bearings through them, and so you can get shaft spinning in places that you want. And another thing is electronics and pneumatics mounting. So you can make a battery mount so it doesn't your battery doesn't shift around, or mount things like Jetsons or your Spark Maxes so they don't get damaged or they don't move out of place. Another thing that we use 3D printing for is custom pulleys. And it's really convenient because you can get pulleys in the size that you want and in the metric that you want. And it's really good for prototyping because you can print them out really fast and see if it's enough, if you get the good ratios that you want. And the last thing is spacers. You can just put spacers in between things where you want to separate stuff, and you can customize your spaces, yeah.
Alright, next up, we'll go into a bit about the most popular types of 3D printers that are used today, and certain types for FRC related purposes, and yeah.
Okay, so the most common type of 3D printing, especially in FRC, is fused deposition modeling, which is FDM. So things like the Stratus and the Ultimaker are all FDM 3D printers, and it's really accessible and cheap. You can get one for cheap, and you can just have it at home. So it prints a thermoplastic from a spool of filament. So essentially, what that means is that it melts like a spool of plastic and layers it on top of each other. And yeah, that's how you get your shape. You have the picture. Oh, that's really sped up, but yeah. And it starts out really hot, and it starts on the base plate, but eventually it will cool down and it will harden into whatever you need it to be. Yeah. And the most popular 3D printers that do this are just right here. But what we use on our team are the Ultimakers and the Stratuses.
Yeah, and Mark Forge is a pretty good printer that a lot of teams use. It's pretty affordable and cheap. And then if you're looking for a really cheap alternative, Prusas and Enders are the way to go if you're just starting a team and you need a 3D printer.
All right, the next one is stereolithography. Well, this is a lot more uncommon, but I think it has a lot of differences compared to the one that we just talked about before. So it prints out of a liquid polythymer plastic, and it's a big pool of liquid, and it uses a laser to harden it. And what's interesting about this is that the prints come out a lot more sturdy and a lot more they come out a lot more durable, and also they're also much more intricate. You can get a lot more detail, but it's not really practical for FRC uses, so most teams don't really use this, and also it's more fun. So yeah.
All right, the next one is digital light processing. Oh, very interesting. Okay, next one is digital light processing. And it's pretty similar to SLA, except when you're not using a laser, but you're using like a different form of light source, and it's usually a weaker form of light source. But compared to SLA, this is a lot faster, and yeah, you can get prints done like within, depending if it's a small print, you can get it done within hours. But if you have a larger print, it takes a few days. But each layer is a lot faster than if you were gonna use SLA, since like each layer could be done within a few seconds. But yeah, the time still adds up if you're doing really big print, and that just depends on like how detailed you want it to be and how like thick you want each layer to be. And the next one is SLS, which is selective laser splintering, and this is also pretty similar to SLA, except you're using a powder material instead of liquid. So like DLP and SLA are both liquid like plastics, but SLS uses like a powder form of like a wide variety of materials, such as like nylon, or like you can even have metals like aluminum. And yeah, this is like one type of metal 3D printer in some sense, because you could. So like how it works is basically it takes the powder material and it splinters or melts it, and after each layer is melted and hardened, the bed moves down and it's covered with another layer of powder, and it repeats the process until you have the whole model finished. And yeah, okay, so going on to, I guess, after we explained all these different printers, like some common materials used in FRC are PLA, ABS, polycarbonate, nylon, and like not often, but like, I guess sometimes you would use metals depending on what your purposes are. But yeah, so like starting from the top, PLA is usually like a lot weaker than all the other materials listed, but it's really fast for prototyping. If you want to get a model out for pretty cost-effective means, you would use PLA, and similarly ABS too, since they're both pretty cheap and easy to make. But ABS, the advantages of using ABS is it's pretty impact resistant. So after making your prototype, you can still use it for like your actual robot if you need to, as like a last resort kind of, or as just a spare part. Yeah, and most of the popular brands that we mentioned before for FDM printers, Prusa, Ender, Markforged, and Stratus, and Ultimaker all have these materials, so you can choose from these. Yeah, and then going on to, I guess, if you want a stronger material for just your main robot, you would use polycarbonate, and we use PC ABS, which is a mixture of polycarbonate and ABS, and that just helps reinforce the material while also keeping it kind of cost efficient, since if you have a whole sheet of whole row of polycarbonate material, that would be pretty expensive to print with. So yeah, mixtures are usually nice because it keeps like components of both. So making like PC ABS pretty impact resistant, which is the quality of both ABS and polycarbonate, and making it able to take on heavy loads. Yeah. And then I guess all these materials are wrapped in spools if you're using FDM printers, which is what most first teams use, since FDM are like, yeah, the most popular ones today, and they're a lot quicker than the other three types that we mentioned. Yeah. And one last thing are the Onyxes. So like if you're planning to buy Markforged printers, Onyx is like the, I guess, main material to use, because it's a lot cheaper to use for the Markforges, and it's pretty strong as well since it's a nylon mixture. And nylon is pretty similar to to polycarbonate and PC ABS, except it's a slightly weaker, but it's a lot more impact resistant, and it also has a lot more, I guess, it's a lot less frictionally. So you can use it for like a lot of sliding parts that you want to just like hinges and stuff that you want to slide around.
Yeah, the next thing is support material. So generally support material are like soluble in water, or they can easily be broken off your main 3D print. And essentially what it's for is to make sure that your print doesn't like collapse when it's printing. So especially in overcutting and overhanging parts. You can see like here, this white stuff is the support material. So if you were to do a regular print on a common 3D printer, since it builds up from the bottom, you would have like areas where there's just nothing there to support your 3D print, and it would just like fall down, and you'd be really sad, right? So you would use support material to fill in these gaps so that the entire thing doesn't just break instantly. Yeah.
Yeah, and next we'll go into some 3D printers we use on our teams, and as Ada mentioned, they're the Ultimakers and Stratus.
Yeah. So the first is the Ultimaker 3 and S3. So the Ultimaker 3s are in our innovation lab. We don't really use them as much anymore. But the S3s are in our new lab, and they're the ones that we just got. Like it's just the newer model that has like a touchscreen and it's better. Yeah. But we usually use them because they're quick and inexpensive. So for parts that don't need a lot of precision, like bearing blocks, or like spacers, we use these. Also, we use it often for prototyping because we don't want to print on our Stratuses for a prototype that we're just going to throw away. And these print much smaller than the Stratus. Yeah. And the general materials that you can put in this are PLA and puff PLA and PVA, but these are the two main ones we use.
Yeah. And for the Ultimaker, PVA is kind of like our support material. Like you can break that off, but often like you can also just use PLA itself because it's a pretty weak material. And even though it isn't actually a support material, you can use it as a support material since you can also just break that off pretty easily. And then next is like our main printer that's pretty expensive and that we use for like large parts of our robot, which is the Stratus. And we have the F370 model. And yeah, it's basically for our bigger prints and the ones that we need to be like that need to take on heavier loads and be impact resistant. So like this year we used it for our shooter hood. Aiden mentioned that before. We also used it for our drum winch for our climber. So yeah, it's like if it's taking on the whole robot's weight, the winch should be pretty strong. Yeah, getting one of these printer is pretty expensive. Like, and yeah, like this was funded by our school. That's why we have like 2 of these right now, I think. Yeah, and yeah, they use it uses GrabCAD Print as its software. We'll mention software later, and we'll show you guys like how we set up our prints on our software. But yeah, using this, we get our strong material like PCABS, and then the support material is QSR. And it's not a chip away material, so you actually have to melt it. Like Aiden said before, some materials are water soluble, but in this case, it's not water soluble, and we have a special kind of solvent for it that we put in a wash for a few hours in a wash away and leave you with only the model that you need. All right, next, yeah, we'll just talk about how to use 3D printers now. Like, I guess how to set up a print on software and then just how to get it into the printer itself.
Okay, so the first thing you need to do is on your CAD file, which is your 3D model. So usually when you print something on a 3D printer, you don't want your holes to be like exactly the right size because most of the time it won't fit and you're gonna have to like open up the hole a little bit more or you're gonna have to reprint it and that's probably not what you want to do, right? So when you export your CAD file, you want to export it in STL, which is what most 3D printers read, and you want to arrange it on your tray bed on like the software. So on the Ultimaker, we use Cura, and you can just like drag around the parts that you want in the orientations that you want. Yeah, and then you select your infill and layer height. So infill is basically just like how much stuff is inside each 3D print because they're not hollow, right? So generally like for stuff that we print on the Ultimaker, 20% infill should be enough, like it's strong enough. So yeah, and then material selection, we usually just pick PLA or a PLA. And then you slice it, and what slicing does, it like visualizes the process of 3D printing. It just tells you how much time it's going to take and if it's going to actually work. And then you save it to your USB or on your computer, and then you can plug that USB into the 3D printer and just press the button on the screen.
Yeah, and then once you have that as a file, you can either, like, I guess if your printer's set up to be Wi-Fi connected, you can send that through the internet to your printer and it'll print right away. Or you can export it as G-code, which is like what the printer file exports as, and then you can put it on a USB and just stick it into your printer and have that print. And then, but before you do that, you should make sure to clean off like old prints from the bed on the printer already, because like you don't want like old material being on the bed and making it not flat, right? If the printer isn't flat, you won't have smooth layers as you want. And also make sure the material in the printer is the right material. Like just check the spools on the back of the printer, or like inside the printer. Make sure it's the right material as the ones that you indicated on the software. Because if it's not the right material, like printing time would be different. And like it also would be melting at a different temperature. So like sometimes it just might not print it, and it would just mess up the whole printer in general. Right, and then next we'll go into like a demonstration of the software that we use
Hopefully
on
I
our
remember how to
team.
do this.
Yeah. Okay. How do we switch over?
This one is that we used.
Where's your HDMI?
Oh,
It's this one.
Oh, okay. Yeah, it is. Okay.
They're connected.
Yeah, Sam set it up. Okay. Yeah. Okay. Wow.
All right, yeah. For people watching the stream, we'll be doing a quick demo of how to use the Ultimaker Cura software.
Okay, so that. Don't know. Okay, sure.
Yeah, we'll be pulling up like a 3D printed part from our robot this year and showing you guys how to set it up on the software. Yeah.
Okay, yeah. So first, what you want to do is you go to your CAD or wherever you're getting your 3D model. Yeah, this is our CAD for our off-season intake. It doesn't have the rollers on, but it's okay because it's just wheels. So, all right, we just have to wait for it to load. So, horrible. All right.
It's
Oh,
loaded.
okay.
Right.
Yeah. So we're just gonna print a pulley. So you select. I mean, you can go like it doesn't really matter where you select it. I'm just gonna select it in the main assembly, and then you have to export it. Oh yeah. Yeah. And yeah, so the part is named here, and the format that you want is STL.
And also make sure that your units are in millimeters. If you're CADing in like imperial units like inches, because we usually CAD in inches, and then but the printers are all set in millimeters, so you want that to be in millimeters for it to work. Because it wouldn't convert the units for you. So you should do that here when you export it as STL.
Yeah. So then you export it, and you just save it where you want it on your computer. The thing should pop up. Okay, yeah, nice. And then you open Ultimaker Cura, and you see over here we have our printer selected. It's the Ultimaker S3, and we used to print it on the 3, but then we got the new one. So yeah, and then you want to drag in your file. So you click on this folder, and then you see wherever you save your file, you can just import it. All right, yeah. So generally, okay, yeah. So you can like rotate your part or like move it around so that like when you have multiple parts, you can print them together and it won't like all overlap, right? So you can just drag them around and see where on the printing bed that you want, and yeah.
Yeah, and also pay attention to like the orientation of this, because like depending on how it's oriented, like the strength of the pulley would be different. Let's say if you were to flip this pulley 90 degrees, like it would be printing it horizontally layer by layer, and that would just make it weaker because it's just in a different orientation. Like if you imagine how the layers are structured, there's a gap between each layer, right? If you're to print it from bottom to up, so you want it to be in the direction where this layer would be taking the least force, so the pulley wouldn't break depending on how you break it. And yeah, and also like before you set this up, you should also make sure your materials are right. And in this case, we print with tough PLA and PVA for our support material, and that's what is in our extruder for our printers. But yeah, and last thing, like I guess you can also change your layer height, which is over here on the top right, and also your infill percentage. And yeah, as we said, the infill percentage at 20% should be enough usually. And like at most, you should do 30% because after 30%, it usually doesn't get much stronger, at least for the Ultimakers. So yeah.
All right, yeah. And then the last thing you do is you just press slice. Yeah, and then it just tells you the estimated time, and then you would save to disk, or usually it would save to USB. But if you have one printed, like plugged in, and then you would just plug it into your Ultimaker, and then you can print. Okay, yeah. Thanks for guys.
Okay, this is going to be lecture hall B, so if you want to stay here for lecture hall B, you can stay here. But then for the other ones, they're going to be in lecture hall A and Innovation Lab. Innovation Lab is on the second floor. Get to know the
Maybe I can just like hide.
So far.
Next.
I can't see where it's going to you don't realize your hall. You want I guess case studies fine. Or you can go through wait, are you going to stay Oh, well, I think you should just stay with me because that's what it affects.
This is lecture hall.
Yeah, that's
This is lecture hall. We can do that. We're going to the restaurant that's wait, which the lab? Wait. Sí, es really so. Going on in there. I think you need
That's why you're using Y and say, yes, milestone.
You told me.
Oh, I need my career.
You need stuff. We'll do it after this.
Okay.
Which computer am I using?
No, it's also like half of it. They're just like gone. I guess.
Until after this.
Yeah.
You get this to work.
Yes.
What's the cable? Hold on. Put it to HDMI and I'll plug this in.
It's HDMI.
Alright, there we go.
To water delivery.
Alright, do you want to get started? Should I get started?
45.
Okay, so we'll start. All right, so this is case studies. We're going to talk about a couple of things today. So what are common types of problems that we see out there? What exactly is a case study? Because that's a defined word. You can see that by it's capitalized. The types of problems. And then we're going to talk about 3 different cases. Brian Air Flight 301, the Fountains of Bellagio, and the Houston Airport baggage claim. But before we get into that, let's talk a little bit about me. I got a bachelor's in mechanical engineering and a master's in systems engineering. I've done FIRST robotics for the last 15 years, which depresses me to know that some of you have not been alive as long as I've done this. A tournament organizer here in Jersey, New York, Pennsylvania, and China. I've been a mentor for STEM for the last 11 years. I'm currently a mentor here with 694 and virtual with 359 in Hawaii. So what are the types of problems? There's a lot of problems that we face every day. And there's a lot of problems that are easy to solve and very common. You plug something in, it didn't work, you plug it back in, and now it works. Some people may know the USB superposition principle, where you plug it in, doesn't work, flip it around, doesn't work, plug it back in a third time when you flipped it back, and it works. Then there's some easy to solve uncommon problems, like maybe your computer blue screen, all you got to do is restart it, or off by 1 errors in programming. And then obviously, if there are easy problems, there have to be hard problems. So some hard to solve problems that are quite common are exams, right? You may have a math exam. It's common to get it, but sometimes it can be quite hard. And then there's some hard to solve uncommon problems. Those might be emergencies. You broke your foot. That's a hard to solve problem that doesn't happen every day, I hope. And there's a lot of unknown challenges out there that are pretty hard and not very common. So there's a lot of different approach methods to problems. On the screen is what's called an Ishikawa diagram. A lot of people call it a fishbone diagram. And what you do is you put every possible thing that could be a contributing factor to some problem, and you throw it up there. You don't care if it's right or wrong, you're throwing it up there. And the idea is you then go through and you say, is this a factor, yes or no? Is that a factor, yes or no? Or as your research goes forward, you can actually cross off entire bones or entire sections of the diagram. Another one is root cause analysis. It's called the 5 whys. So let's say we have a problem, and the problem is, I couldn't get to school on time. Well, then you ask yourself, why? Well, I couldn't get there because the trains were delayed. Why? The trains were delayed because there were signal issues. Why? The signals are really old here in New York City. Why? We don't have enough funding to upgrade them. Why? Because we don't have funding because people don't use the train system. It's like a little circular there. So that's one root cause analysis. Observation interviews. Sometimes the best information you're going to get are from the people who are on the ground level dealing with the problem. So there's often a little bit of a ivory tower issue with some companies where you have your executives and your management sitting up in an office away from where the production's going. And they have no idea what the problems are. It's only after asking the workers who are there, hammering the nail in or screwing the bolt, that you actually understand what the issue is. There's a lot of different methods. These are just some of the 3 most common. So what is a case study? I said it's a defined word. It's a research approach to create an in-depth, multifaceted understanding of an issue in a real-life context. And this is used all over many different disciplines: business, engineering, medicine, biology, psychology, etc. So a lot of people, you've heard of studies or you hear on the TV a research study. They are actually doing case studies. They're actually trying to find out why things happen the way they are. And there's a bunch of different ways of doing it, but let's kind of jump into our first problem of the day. And this is where we have a little bit of engagement. The more you engage, the better prize you'll get from me. So Brian Air Flight 301 is a flight from Puerto Plaza, Dominican Republic to Frankfurt, Germany. It took a Boeing 757 and was flown by a crew of 3. Generally, they're flown by a crew of 2. And the aircraft was stored on the airfield for 20 days before they used it. Very basic, here's the introduction of the problem. But this is where we actually enter the problem. They took off. The flight took off normally. They had no issues with it. There's a thing in airlines where they call V1 and V2. V1 is where the flight has the first opportunity to take off, and V2 is when there's a point of no return. You have to take off or you're going to crash. So they hit V1, they take off, they rotate, they get into the air, fine. As you may know, the flight takes off, it has this upward trajectory, and then it starts to level off. And that's when pilots typically engage the autopilot. So about 90 seconds into the flight, the autopilot is engaged, and they're cruising. 10 seconds after they engage the autopilot, warnings on airspeed and rudder pop up. They're flashing. And if you've ever seen videos of a cockpit, they're actually like beeping at you, bong, 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 and they're flashing in front of your face to try to get your attention. So the captain and the first officer are sitting in two different seats with their own sets of equipment. And the captain airspeed indicator was reading 400 and climbing, and the first officer was reading 200 and declining. So they're telling you conflicting information. You know, additional warning lights and sounds and stick shaker. Stick shaker is just an alert to say the plane's going to stall. They're flashing at it. Then about 30 seconds afterward, the flight crashes into the ground. Everyone is killed. So, with that fun story, anyone have any idea what may have happened? What's up?
Maybe because it was on ground for 20 days, they didn't check it before.
That's a good point. The flight was on the ground for 20 days. No one's checked it. You know, maybe that's a contributing factor. That'd be a piece of our Ishikawa diagram, right? What other reasons may have been? Yeah.
I know that airline in particular had maintenance problems, that they were sort of negligent keeping up with their planes.
Yes, see, someone's done research into the background of this plane. So, yeah, there were some negligent and problems with maintenance. You know, you always want to make sure that the flight you are going on has a good maintenance and track record, right? Any other things? Yeah?
Their equipment might have been faulty because they're sharing like opposing information. So something.
Yeah, equipment might have been faulty. Maybe that's, you know, the 20 days on the ground. Maybe they're related somehow. So, you know, we have these many different, you know, ways of looking and approaching a problem. And now we're going to kind of, that we discussed, we're going to kind of go a little bit on how they try to solve it. So many countries have their own transportation safety boards. We in the United States, we have the NTSB, National Transportation Safety Board. And if you ever get bored and you're really like, you want to find a problem or something, you can actually go on their website and they actually say their biggest product is producing reports. You can actually read these reports, and it's about trains and planes and cars, and they actually tell you what the problem was, how they try to solve it, and what they think the root cause was. Airplanes have black boxes. The only way we knew about that airspeed indication was because the black box recorded it and we were able to recover it. And, you know, we did this, you know, in almost minutes, right? But this took them months to figure out something. It could take them an entire month just to find out the airspeed of one instrument. And when they did this, they scavenged the entire crash site and they tried to trace and track every little bit of wreckage because you don't know, even if the smallest thing could be a big clue. They documented everything with video, photos, written notes. They interviewed people. They interviewed families of the pilots to try to understand what the mindset of the people were. And again, you never know what the smallest detail can put the whole thing together. There's actually a lot of, you know, famous, infamous photos of NTSB and other related agencies. When they pick up things, they actually take photos of it, they circle it, they index it, they serialize it. So you may think of a window on a plane that has maybe 16 bolts on it. If they find the plane window with the bolts in it, they actually count and serialize each and every single one before they take it out to analyze it. Because you don't know if, you know, a bolt on one side versus the bolt on the other side, maybe there's some relation in the patterns. So with this problem, you know, the Dominican Republic General Directorate of Civil Aviation, which is their NTSB, actually said that the crew's failure to recognize the activation of the stick shaker as a warning of the stall and the failure to execute procedures for recovery of the onset of the loss. And the pitot tubes, we're going to talk about that in a second, were never recovered, but they were believed blocked by insects. So kind of like what you were saying, the leaving it on the ground for 20 days had an issue, and what others were saying about perhaps some of the equipment was faulty. And the captain's instruments governed the sensors of the autopilot. So what does that mean? It means that the programming, the logic, is not smart enough to detect if there's a conflicting answer, which meant the humans had to figure that out on the spot while all the warnings were flashing at them. And I don't know if anyone's ever been like on maybe a roller coaster. Have you ever tried to like do a math problem on a roller coaster? Your mind's kind of preoccupied while being on the roller coaster. Or maybe you're in like a really, really tense thing. You can't really think. There's a saying in psychology that when you're panicked, your thinking capacity drops by 50%. So it's different us thinking in this classroom versus them actually living the problem. So this is the engineering part of this. You know, pitot tubes, they're used to determine airspeed. They use Bernoulli's principle, and we're not going to really dive too deep into it. But I will say, when I was younger and I saw pitot tubes on airplanes, I used to think that they were like machine guns or something. So that's what they are over there on your right side. They look really tiny, really benign, but they actually have covers that's supposed to go on them when they're in storage for a long time. So the lessons learned from this flight was that if you have two sources of data that's the same thing, that the data should line up. And if not, a warning should be produced that a mismatch is there. And that's one of the critical flaws, that if software was doing it, the humans didn't have to do it. And that means they didn't have to figure it out on the spot. And that information overload to pilots and drivers takes away from that operation. And the small details matter. We may think, oh, don't put the cover on. It's only a few days. It's no big deal. But, one wire could lead to failure. One screw coming out could cascade to a whole part falling off. I'm sure many of us, while we're building our robots and competing with them, may see our robot stop moving only to find out later the battery wire came out. It's those simple things, right? And this is just on a bigger scale. And nowadays, the FAA explicitly told Boeing on that plane, on every single plane after, there has to be an explicit warning message to tell you if instruments disagree. And furthermore, every pilot on the planet that learns to fly a 747 or any type of large jet has to learn this scenario exactly. They actually pull this up. So, and this goes on to this continuous and endless improvement. We're always trying to make things safer, things better, things faster, but we can't, also sacrifice, safety while trying to make things bigger, faster, and whatnot. So that's our first problem. What do you guys think? Hearing nothing means everyone's okay because no news is good news. All right, the Fountains of Bellagio. This is one of the largest fountain shows in the world. This is actually the largest until the same company who built it built another one in Dubai. It cost $40 million to build in 1998. Fully computer programmed and timed to music. The water jets gush out 13 feet into the air. Fun fact, birds actually don't fly over the fountain because they've learned to not get hit by the jets. Every half hour till midnight, and it's a free public show, which is something that I like, it's free. So, if you ever go to Vegas, highly recommend it. I've actually seen it, it's really cool, speakers are really loud, it's really nice. And now they have new jets, so they're even better. So, the problem. The fountain nozzles would go out of surface rapidly, much faster than the manufacturer would claim. And when they would test a bad nozzle on a test bed, it would work just fine.
Howard? Wait, if you do it like this, the stream only sees it like this. Is it possible to make it like?
It's fine like this.
Okay, sure, whatever.
Why do the nozzles fail? Any ideas? Yeah?
Maybe about the environment. Okay.
Could be the environment.
You mentioned they were shooting 13 feet up. Maybe that was too much PSI with pressure.
Maybe it's too much pressure. Maybe it's too high.
There's too many systems working at once when it's on flooded.
Oh yeah, there's so many integrated systems here. What could be the problem? Even a small wire again could cause a cascading problem later.
And because so many things working together, maybe something messed up.
Yeah, maybe again, that just like we said, one small thing on something else could lead to a problem somewhere else. Any other ideas?
Or maybe one water stream was supposed to go to one specific pipe that ended up going to another.
Yeah, maybe the pipes got crossed. Any other ideas? Any other questions? Anybody want to kind of trigger, like, how do you think they solved the problem?
How do you test something like this? Like, how do you test if there's a problem in the first place without sacrificing lives?
So think of a motor, right? A lot of people complain about the QA of a certain company in robotics. But theoretically, when you get a motor, they're supposed to test it at the factory and at the shop before you buy it, you get it, right? And they usually have a test bed where they'll plug in the motor into some, already set up thing, plug it in, hit a button, and then it spins, right? And you're kind of proving that it works. Take it out, package it up, send it off. Yeah?
Just the nozzle underwater.
Do they test the nozzle underwater? So the nozzle actually it's just underwater. It actually peeks out just a little bit, almost like kind of like a scuba diver where they have the air out. Because if you try to shoot it under the water, you're kind of going to dampen the effect. So to your point, yes, they do test it in a bed of water, but they don't test it in the 5 feet deep fountain that they have out there.
Because they don't want to risk losing your fountain.
I think it's more just the test bench setup of having everything that you would want to diagnose there. I never actually saw their test, so I can't say for certain. Yeah?
Maybe it was the weight of the 5 feet of water on the pipes. Bringing water.
Yeah, maybe there is an environmental difference between their test bed and what the actual fountain looks like.
The manufacturers lied about making.
Yeah, there is a lot of that out there. Claims are not as what was expected.
It's like when you test one motor on like a testing motor versus testing motors all working together on a robot. It doesn't necessarily mean that mobile will work with all the systems are together.
It's true. So let's talk about a little bit how they tried to solve it. So they would send divers into the fountain to retrieve and replace the nozzles because you want the show to go on, right? You got to put a new one in there. They would take it back to the lab and they would test it on a test bed, and it would always test fine. You know, they could never find what the issue was. They're like, maybe there's debris in it, maybe there's something. So then they tried opening it underwater and they saw nothing. And then finally, they asked the divers who were installing and servicing the nozzles, and they reported a cold water feeling while working on the nozzles. And just remember, Las Vegas is a desert. So if they're feeling extremely cold water while the sun's beating on them all day, there's something going on there.
Was the pipe faulty and water perhaps so the pressure was lower?
Maybe. So let's talk about the problem itself now that we kind of understand how they try to solve it. So ice crystals were forming inside the air valves from the extreme pressure drop of 200 psi. So again, psi and trying to do this new thing was a contributing factor. The manufacturer never before used anything over 100 psi. Remember, 13 feet in the air. I can't even, like, if I wanted to throw something 13 feet in the air, I couldn't do it.
It's too much energy.
Yeah, it's a lot of rapid energy. So there's this thing called the refrigeration effect, where there's a difference in pressure can lead to rapid expansion and lower temperatures. We tend to think of things, hot and cold, but there's actually a whole physics principle that we could talk about in another lecture about that. And this same process, you use it at home for your refrigerator. Your refrigerant expands and compresses, and when it does that, you can have these hot, cold swings, and it cools your food or whatever in the refrigerator. Now, the nozzle I have here is of a water jet, but it's the same basic principle, just flip it around. Instead of using an abrasive, they put air in there to kind of really help propel the water forward. Yeah, you have a point?
Well, my question was, again, how do you test this? Because I feel like you should test this in a similar environment to where you can get your final product.
That's a true point. You always want to test a similar to your thing, but has anyone had their robot work at home and then not work on the field? Right? You can't, if you wanted to buy a field, that's over $100,000, right? Sometimes you can't always replicate the exact conditions that your product or thing or system is going under. So you try to replicate it as best you can, and you try to document the differences, but you can't always get it 100%. And that's where one of these key differences between not exactly the difference in environment, but the actual moving it from that environment to your test bed. When they opened up the nozzles to try to see what was inside, the ice crystals will melt and destroy the evidence that was showing that it was being blocked. So that was the key problem here. So what was the solution? The manufacturer changed the location of where the air and water mixed to give them more volume if ice crystals were to form to melt. And they changed the feed so that the pressure difference over the nozzle was lower. Failure rates dropped. There's this thing in failure analysis called MTBF, or mean time between failures. When that time goes up, failures take longer. They're less frequent. And then they have a new style of nozzle today that shoots 5 streams of water. It's really cool. It actually twirls as it's going. It's really amazing. Has lights, XYZ movement. But when they created these nozzles, they actually remembered this problem because they've already faced it. And now, again, we're always striving to do better and better. So that was our second problem of the day. What do you guys think? Some of these people, when they're solving it, it's not a single person sitting down and trying to figure it out. There's a whole team of people with different disciplines. Maybe it's the water. Maybe it's the property of the water. Maybe it's the nozzle. Maybe it's the electrical system. We don't know, but we need to get all those people in one room to talk about it so we can try and figure out where the problem is. All right, our final one of today, the Houston Airport baggage claim. So Houston Airport's a hub for United Airlines. They have multiple terminals, A through E, domestic and international flights, over 45 million passengers before coronavirus, including for the first championship. I hope to see some of you at that airport. And fun fact, it's owned by the city of Houston, Texas. It doesn't have its own separate group. So airport, what possible problem could we be talking about today? So they faced huge numbers of customer complaints about baggage claim wait times. And what does that mean for them? Because they're just an airport, right? Get your bag, go away. You could risk their ability of being a prime destination if people can't get their bags and go on vacation or transfer. Or worse, they could lose their airport rankings. So that would mean less people want to come, which means less revenue for the city, why are we having an airport then? Now, executives were trying to seek ways to improve times for customers. So what would you guys do to try to solve the problem of baggage claim wait times? Yeah?
Well, usually in the airport, it's like a conveyor belt, right?
Yeah.
Where there, So either the conveyor belt is moving too slowly or it's stopping at random points. It could be many issues, but the first thing I would think about is the main source, like how are you getting the baggage in the first place, which is the conveyor belt.
So how do we make the conveyor belts more efficient or faster? Yeah?
We can have more conveyor belts in different areas.
We can have more conveyor belts, although it does add more complexity. Yeah? You're gonna need to speak louder.
Big one sorting system.
We have a what, sir?
Sorting system.
We could use better sorting systems. Yeah.
Make the conveyor belts faster but also longer. So bags come out faster but stay out at the same time.
We can make them faster, longer. Yeah. We can do a change to the airport design. Any other ideas? Yeah.
To streamline the process from when like the flight attendants like take the bags from off the plane. Like,
We could streamline the process. But what do we do to streamline a process? How would you do that?
Well, usually it's like I'm not entirely sure about an airport, but then whatever. So like on an airplane, like passengers get off, and then I think you take the baggage off, like the plane. So like you could use like a separate. Sorry, I'm not sure. Like
So no, it's a good point, right? Maybe there's some other equivalent process somewhere else in the world that we can maybe try to replicate or make more efficient or adapt to our needs. Any other ideas?
There's probably like inefficient communication between the people who are carrying the baggage off the plane into the airport or
Inefficient communication. How hard is it for me to sometimes get one person to talk to another person? It's like, guys, just pick up the phone.
So that wouldn't even be a mechanical issue, that's just a social issue.
Oh, maybe you're right. Maybe it's not a engineering or a mechanical issue. Maybe it's a social or human issue, right? Maybe they just gotta talk. So one of the ways that the executives tried to solve the problem was to hire more baggage claim attendants and hire more people to help get the bags off the plane. And when they did that, they found that their times went from about to 8 minutes, which is an industry standard. Almost anywhere you go, they try to strive for 8 minutes from when the airplane lands to first bag into the carousel. However, when they did that, complaints still persisted. So maybe engineering is not the right way. Maybe there's something else. Anyone have a better idea that isn't particularly an engineering idea? Yeah?
maybe the people are just like going straight to baggage. Maybe people in the airplane can have no merchandise or shops. So other people are
That's a good point, and you're leading us into this next image. So I know this is hard to see, but I kind of took it right from their website, so it wasn't really made for us. This is a picture of the airport, and over here is where the gates would be. You got your security thing, and then they would go down these escalators to get to baggage claim. So, to your point, right? Maybe there's something that we could do here to solve the problem. Any ideas?
Maybe like they take people off the plane, they go to baggage claim afterwards. So maybe you want to like maybe hold the people on the plane for longer, or
Maybe we can leave them on the plane for longer, yeah.
We'll have the security first and then the baggage them at the end, and then they can, so it gives more time to, like.
So security is when they're going into the airport, not when they're getting out of the airport. But no, maybe there's something to do with TSA, because we all know TSA is the most efficient thing in the world.
Yeah,
So-
totally is.
Yeah.
Here's one question. Is baggage claim all in one area with all the same different flights? Or
Per terminal, yes. So I don't have that particular image on this slide, but you'll see in a little bit that the baggage claims are next to one another. So let's get to the root of the problem. We're all kind of talking about symptoms, but let's talk about the root of the problem, and that's waiting. There's this thing called active versus passive waiting. Active waiting is when there are things that you can do while you're waiting for the preceding thing, and then there's passive waiting when there's nothing else you can do but wait. And the way I like to describe it is, all of us took public transit, or most of us took public transit to get here. How long would that ride, train, bus, whatever, feel if you didn't have your cell phone to do something with?
Like a century.
Yeah. So, but because we have our phone, I played video games on my way here today, and I almost blinked and I was there. But it really took me 90 minutes to get here. If I were to do nothing for 90 minutes, I'd be pretty bored. And then I'd also complain about how long the bus would take. So, active versus passive waiting, is there something that we can do to these people so that they're not passively waiting, they're actively waiting? Any ideas? And then I'll show you the answer. Yeah.
Whenever you go to an airport, there's a lot of shops.
Yeah?
Specifically when you go to different countries. Like when I traveled to Dubai last year, there are many shops that I've never been to before, many different exotic foods, toys, stuff like that. I guess, and I was pretty much bored in the airport. I was there like, I don't know, 7 hours for my flight. But all the shops kept me occupied. And the second I heard that we're taking off, it felt like 1 minute at time.
Yeah.
Because that's how, because humans are active creatures, we're social creatures.
You know, it's an interesting point. Those duty-free sales, there are now airports designed to force you to walk through those shops to try and get the most bite of the apple as they can.
Have you ever flown into Heathrow?
Into what?
Heathrow.
Heathrow? No, I haven't.
That's the worst one of that.
Yeah. So it's designed into it now because they know it makes money. Yeah.
You can do attractions like in Las Vegas. They have these little slot machines and stuff, so that can make people stop.
Yeah, we may have to change the local laws and county laws to do that, but maybe that's an idea.
You can have like entertainment centers, like a play area for the kids or sightseeing or.
So a lot of the recommendations that we've just said, you know, they require time, money, budget, effort, and you'd have to shut down part of the airport for some of it.
I mean, every problem or every solution to a problem kind of does require that.
Oh, wait till you see what they chose. So the red line here is a line that they took prior to the instrumental change that they made. And to kind of make so that people can see, you're starting here, you're traveling towards the escalators, and you immediately get to the baggage claim. So that was, let's call it pre-change. Afterwards, they instituted a new policy at the airport where they tried to get arrival flights to be further away from the baggage claim. So instead of being right here, they're all the way out on this wing here. And now they have to travel all the way down across the airport and across the baggage claim to get to their carousel. So remember what I said about active versus passive waiting? When you're walking somewhere, you're not really passively waiting. You are the reason why you're not there yet. You are doing something to get there.
Like you're the active force.
You are the active force, yes, to get there. And what they found was, when you tried the red line, it took about, let's call it 2 minutes. And then you spent 6 minutes passively waiting. But when you took the blue line, you spent 6 minutes actively waiting and 2 minutes passively waiting. And the really, really fun part about this is they made no changes to the airport other than their general policy of where flights should arrive to. And they were able to take their complaints down from super negative to 0. See, yeah, we got to give them a round of applause for that one, right? That's innovative thinking right there. So,
you can correct me if I'm wrong, but this is kind of like cognitive dissonance. Because like, you know, we humans, we're kind of just, we don't like boredom. Boredom is kind of like disgust to us. And of course, just waiting passively is boring. So I guess from a psychology point of view, they kind of thought, well, if we just make them, I don't know, work for themselves or make them entertained, they won't give us negative reviews.
So yeah, there's a whole element of psychology here. And when they stopped thinking of it as an engineering problem and more as a social human problem, a different set of solutions existed that didn't cost them any money and took their complaints down to 0. So let's talk a little bit about kind of what they call critical path. It's often a project term or program management term that's used, and it defines the tasking that requires the most time from start to finish. So here we have multiple tasks that have to be done. There's kind of 3 branches here, but the critical path actually takes A, D, E, and takes a total of 9 days because D and E can't start until A finishes. But in parallel, task B and C can occur. They take 6 days. So the critical path here would be A, D, E, and any other path. It doesn't really matter. And you can actively wait if you're not on the critical path. You can actually spend some of your time doing something else because no one else is waiting for you. But don't take too long, otherwise you're going to become the critical path. Now, what does this mean in the real life? When you're working in the workplace in an engineering firm, if you're on the critical path, you're doing basically, management reviews almost every week to show like, what are you doing to stay on time? But if you're not, they're off your back. But when you take too long, they start getting on your back. Why are you taking so long? And what does this mean for robotics, right? Perhaps task A is building the robot, and maybe task B and C is programming the robot. You don't actually need a physical robot to start instantiating motors, figuring out what your autonomous might look like, figuring out maybe some equations or formulas that you may want to use for a shooter speed or an intake or something of that sort. There's a lot of different things that you could be doing in parallel. I often hear a lot of teams complain that software has nothing to do until the robot's ready. False. Fake news. It's not true. They're lying to you. There's always something that you can do.
Isn't the software basically the brains of the robot? Obviously, the body can't work without the brains, and the brain can work by itself.
So if we have more time afterwards, we'll talk a little bit more about that, but I want to get through some of these slides. So to wrap this up, trying to handle this as an engineering problem didn't really impact the negative feedback. They hired more people, they tried to make the baggage claim more efficient, but they still saw those negative reviews. And oftentimes, because of those solutions, if I make the carousel faster, I don't know what speed it was before. If you're making the handlers better or higher, I don't see that because I don't interact that with them. So those solutions are unseen solutions. But when it was handled as a human behavior issue, solutions required minimal investment. They had to do no changes to the airport. So to wrap up this entire thing, there are people who dedicate their entire lives to understand why things break, why failures happen. And there are lessons in these failures so that we don't repeat these mistakes. That whole idea of changing the airport design, now people instrument that to make more money out of people as you wind through those shops. The system can be robust, but human inputs can cause these failures. So we saw with Brian Air 301, it was actually humans that caused the issue, but they didn't realize it because the system inputs were so messed up for them. And now we have safeguards. Now it tells people if there's an issue. And you can do training, you can do labels, you can have features designed in or out. And just because one flight crashed or one airport had an issue, they didn't stop. They kept going. Don't stop once just because it broke. So with that, I'm going to kind of end with if anyone has any questions. But before that, if people want to learn more, they can find these slides. These are some links that they can take a look at. So questions to wrap this up.
Could you talk more about, are there particular ways a mechanical electrical programming robotics team actively implements these? Is there like a rubric or a formally, or there's just ideas in the back of the head?
So there's a couple of tools that you can do to actually do project program monitoring, which calls out those critical path elements. And you can actually say, path branch 1 is mechanical, branch 2 is electrical, branch 3 is programming. And you can say, hey, mechanical, you need to be building a base so that we can have electrical who's already trying to work on those electronics, crimp them, strip them, get them ready to just slot in. And then you could also have another branch of coders who's, hey, we're going to have 8 motors, they're going to be of this kind, start instantiating them and start thinking about these are the different ways we want to manipulate the robot. So there's a couple of different things you can do. If you want, we can talk more offline, because I think we're basically out of time here. All right. Thank you, guys.
Did we start late?
Yeah, we did.
Because this is posted.
30 minutes long, right?
Yeah, it's
Oh, it's a whole hour?
Yeah.
Yes.
Oh, I thought we had, okay,
No, it's
maybe
not
we do have
30
more
minutes.
time.
You have an hour.
Oh, I have an hour, okay. So, okay, we could do more questions then. I thought all those people out there were waiting for us. Okay. So, to kind of more directly answer your question, anytime someone says they have nothing to do, I think that's fake news. So, you're going to need bumpers. You can have people start making bumpers because you should know what your robot size is going to be. You can have people starting to get the electronics ready because you know what electronics you want to use. You can have people start figuring out the overall design of the robot. And what a lot of teams do is they build the drive base in parallel to their end effectors. So let's say they need a claw or some type of roller arm, right? Someone's building that while they're building the base. And programming, now that you know all these are happening, you can start to say, okay, motor 1, 2, 3, 4, those are drive base. Motor 5, 6, 7, they're going to be the end effector. Motor 8, that's just going to be a simple solenoid. Any other questions?
Could you touch on the troubleshooting parts as well? Like,
Okay.
you're at a competition or in the lab. Is there a formal rubric for We mentioned a lot of different possible solutions to
So, troubleshooting, right? There's a lot of different ways to attack a problem, and obviously, you can do it in a couple different ways. Just want to try and get this back up again. So,
Well, I have a pretty simple question. When you come up with an idea for a new invention, how do you start off trying to actually use it?
So there's a couple of different ways to make things, right? Let's kind of focus in on the world of robotics because I think that's the most relevant for everyone here. So let's say you have an idea, you have this new elevator design, right? There may be a couple of things that you may want to, prototype. So a lot of people, I'm a huge advocate of wood and cardboard prototypes because they cost a lot less. You could use a drill as a makeshift motor instead of having to, get power, wire it up, put it all up there, code it, and just have someone with a drill holding it in place. Cardboard, really great, flat surface to kind of mimic sheet metal. Wood to mimic, long extrusions. So there's a couple of different ways to kind of attack that. And then it's being diligent with your design, right? If you see something that works, carry it forward. If you see something that doesn't work, move on. One of the biggest things that I think people sometimes forget in the world of robotics is some people create these ideas and they're really kind of outlandish out there. And some of them are really good, but then you find another idea that works better and they don't want to give up their own idea. One of the biggest lessons I learned in robotics is if you have an idea, you have a thing, being able to discard it and accept the new idea. Because sometimes we have attachment issues a little bit, and you have to kind of give up your design because something works better.
Because we're prideful, we want to.
Yeah, a lot of people are a bit prideful, and there is something to that, right? Your design made it to a robot, right?
And feel proud.
Yeah, but at the end of the day, if your idea doesn't win a competition, you're going to shoehorn your entire season.
Yeah. And you got to acknowledge that other people might have better ideas.
Yes. Yeah.
I have two questions. What are some other techniques besides the ones that you listed you think would be helpful?
Other techniques in terms of what?
Just like problem solving.
Problem solving. So the thing about problem solving is it's kind of like if people like spicy food. The more you problem solve, the better you get at problem solving. And the more you like spicy food, the more you eat spicy food, which makes you want to eat more spicy food. It's a weird, deathly circle spiral. So ultimately, right, a lot of you are very new at this, right? You haven't seen many problems, you haven't done many problems. But as you kind of go through the seasons, right, as you talk to older and older members or maybe veterans or alumni, right, oh yeah, we always had a problem with this and this is how we did it, right? So it's kind of going back to that slide that I said before of types of problems. Easy to solve common problems and uncommon problems, right? You may get a blue screen. You don't know how to do it, but someone else has seen it before. Restart the computer and plug this in or something. So having that repertoire or history of problems is one thing. Another thing is Googling the problem, right? Just look it up on the internet. We have the power of the internet on our phones right now. People don't realize this, but whenever I try to solve issues at competition, I just Google the problem and then people talk to me like I'm a messiah. I'm like, no, I just looked it up. Or my favorite, hey, we have a problem with their motor. The controller's blinking in this way. We don't really know what it means. And then I just look up the documentation from the manufacturer and it means this, do that. Like, oh, how did you know that? I just looked it up. All right, what's your other question?
A common problem that you experience in rookie teams, like problem solving,
Oh, no, problem solving is a universal problem. The only thing rookie is that they don't have that history, but it's the same thing because 1/4 of your team is always new every year, right? People are ideally matriculating, graduating out of high school, and then you have people coming in. So 1/4 of your team is always going to be new, minimum. Other questions? So I want to talk a little bit about programming in specific because that tends to be the people who always cry the loudest that they have nothing to do. I always have a problem for some reason when we start programming the robot that the Robo-Rio isn't updated, the gyro station isn't updated, things aren't at the latest revision, and then you go to competition and, oh, we need to spend 3 hours updating everything because it wasn't updated. They should be monitoring the releases from WPI Lab or from the manufacturers for the latest firmware and for the latest releases because generally when you get to competition, you need the latest stuff. or it won't work on the field. And then you're spending 3 hours at competition not practicing but flashing all of your different devices. So that's one thing they definitely can be doing. Another thing that they can be doing is, you don't want to start with a blank piece of code on week 5. Week 1, 2, 3, they should already be starting to create what I call null autonomouses and null things. So I lost a world championship in 2011 because we never wrote a null autonomous. Our programming team was so haughty that, we will never need to not do this. Well, it turns out on Einstein, we needed to turn off our autonomous to let another team do it because they did it so much better than everyone else. So we turned it off, and that broke different parts of our code in our robot later during teleop. So first thing I always do now, we write a null autonomous that does nothing. Second thing we do is then we write a null teleop that does nothing, and we use that typically to troubleshoot autonomous mode so that we don't accidentally break something later. Another thing that we like doing, or I like doing, is I call a shoot forever mode. I call these debugging modes where the robot's just set up to kind of intake and shoot the ball forever, and we use this to kind of tune in a shooter. So you have a ball, you keep feeding it, it's always shooting, and then, that's too much, lower its speed. That's too little, raise its speed. And then have little buttons to do it so you don't have to recompile. I call those troubleshooting modes. Those are things that you can do without the robot. And then finally, I tell programmers to learn more programming. There are so many free resources online that you can use. So there shouldn't really be ever a dull moment in programming. There's always something to learn because I know they're not expert, master, dojo, programmers out there.
Isn't code always evolving? I mean, technology is always getting better.
There's a reason why it's called computer science, right? It's actually not that reason, but it's still an active area of research. People are still figuring out better and faster ways of doing things. Any other questions, comments? So since we have more time, we can actually talk a little bit more in depth about the airport problem. So this design, this case study was studied by many other airports, and they found that by just changing a few things, they were able to change the way humans reacted. And another really fascinating one is the London Tube, their MTA. They actually have signs that lie to people. They actually tell most of people to go a different way, a different path, because the entrances and exits there are bigger, so that the majority of people flow in one direction than another direction. Because some of the little pathways, if you will, they may get you there faster, but if more people take it, those pathways don't work. So there's actually an active area of research of human behavior, of how do you inform people something to make your overall system more efficient. And does that mean you tell people inefficient things to make the overall system more efficient? Because if you were to try to change those entrances, it requires millions of dollars to do it, and you shut down a station while you're doing that. So one of the problems with the MTA is because it really is like the lifeblood of New York City. You can't just close stations on a whim. You have to do as much of your effort on the weekends or on downtimes as possible. There's no other transportation system in the world that's as big, as popularly used as the MTA, that runs 24/7. A lot of people talk about, a lot of Asian networks like the Tokyo system and, China and Korea. But those systems, they close at a certain hour of the day. They have a last train. When's the last train here? No, it's 24/7. There is no last train. Service just gets cut down. So, there's a huge active area of research, not just on solving it with an engineering solution, but solving it with a human engineering solution. Yeah.
What's the problem that the MTA has that you think can be fixed with one of your solutions that you discussed?
Probably the biggest thing is adding a line that allows people to go from different boroughs without having to go through Manhattan. Because if you're able to kind of, let's say, and I'm not the best at New York geography because I don't come from here, the Bronx and Queens, they're next to one another, right? They're not through Manhattan. If you were able to get from the Bronx and Queens without having to go through Manhattan, you could cut down times by like 2 hours, and then you save all that capacity for the other trains. So now you're making trains faster because you don't need to wait for as many people. Yeah.
So in robotics, like everything is based around the team, and when problems arise, you have to face the other team. How would you go through with communication within sub teams and just communication overall, how to improve that?
So what we do on 694 is we have this thing called precaps and recaps. Precap is telling everybody what are the objectives that you have for the day? What do you expect to do? And the recap is what did we do? And for me, sometimes I'm not able to get to the city because every time I come here is $20 and 2 hours of my life, minimum. So what I use is I look at those precaps and recaps and I look, did they do what they expected to do? What problems do they have? And if they have problems, what can I do to try and solve those problems? Is it a research problem? Can I just look up the documentation like I said before and tell them this is how to fix it? Or is it a problem with communication of this sub-team is not talking to this other sub-team? And if that is the problem, how do I get them to engage with one another? And more directly, if people aren't doing what they said they're doing, why? What's going on? Did something happen? Did they have to go home for some reason? What is causing that delay? And now it's giving that visibility to kind of everybody. Now everybody knows. And now, because everyone knows, you can hold those people accountable because, hey, you said you were going to do this. Why didn't you do it? Got another question out there somewhere? All right, because we have more time, we can actually talk a little bit more about the Vanza Bellagio. So the new nozzles that they actually have 5 exits, and they have different types. They have these high jets that go 13 feet in the air, and they have these smaller ones, and they have colors. And now, a lot of amusement parks, they actually use water shows. They actually spray the water up into the air to create kind of a backdrop, kind of like a screen, and then they project right onto it. Disney's adopted it, Universal's adopted it, Vanza Bellagio's adopted it. And it's that continuing, evolution of technology. What's really amazing here is that there's only been 5 cancellations of the show in its entire history, which is incredible amounts of uptime. They actually have a special barge that they have that goes onto the fountain to try and service these things during the day so that at night they always work. They have a whole team of like 19 divers that are just dedicated to just doing this. Yeah.
Would it not have been easier to just heat the nozzles?
So now that you're heating the nozzles, you're actually changing the properties of water and properties of air, right? If I took like a phase diagram of temperature, pressure, when you heat water, it undergoes different expansions and compressions and different changes of phase, whether solid, liquid, or gas.
So the show would be as impressive?
It may not be the way they thought it was. A lot of people, they like to avoid making rapid changes to things because if you induce too many changes, you may have a lot of externalities or different changes that occur at the end line. There's this idea of like a black box system. When you put in too many inputs or too many changes in it, your output sometimes rapidly changes. It's sometimes also called the butterfly effect.
And when you make too many rapid changes, there's not enough time for whatever's being changed to adapt to that.
Yeah. Now, that would be a huge engineering change and would probably change the delivery date. A lot of contracts, especially for things like this, if you're late on delivery, you may now have to actually pay your customer instead of them paying you. Because they have other contractual agreements saying if you're not done by December 1st, because we need to have this show December 10th, you're paying us for those unexpected cancellation fees. Yeah.
So if you have a bunch of solutions, you should first do the simplest solution. Yeah. If the simplest solution works, then you don't have to do any of the other solutions.
Yeah, there's this thing in troubleshooting called invasive and uninvasive solutions and testing. So an uninvasive thing would be you don't change anything in the system, but you change maybe an input or an output or the way you look at it so that you understand a little bit more without possibly changing or damaging the system. And then there's invasive things. Maybe you have to open it up and then take something out and replace it. And now you've kind of changed the system and now it may not work the way you thought it did. There's a huge thing in engineering firms and products where you need to fix something in place, but you need it to have the exact same outputs, the exact same function. And they're like, how can you fix this without touching it or shutting it down? And that's where those invasive and uninvasive solutions may occur. So the great thing I like about mechanical engineering is that I learned a lot about these different types of properties of mechanical properties, physical properties, and electrical things. And then what I like about systems engineering is it gives you a different way of thinking things. This Ishikawa diagram, the critical path thing, those are things I learned through systems engineering and that I use in the workplace. And the thing is, I'm not, specialized in electrical or coding. I barely know how to code, but I understand how coding works. And it's because of that history, that knowledge of stuff that I'm able to kind of apply what I know to things that I see. And that's why every time there's a problem, I just Google the problem and people tell me I'm an amazing person. I just looked it up. I have the power of the internet in my fingertips right here as long as it's charged. Yeah.
Do you think for those reasons engineers make good leaders?
Yes and no, right? Because Steve Jobs, right? Famous person, ran Apple. Does Steve Jobs know how to code? No. Does Steve Jobs knows how to engineer something? No. Does he know properties of silicon? No. Does he know how a conductor works? Maybe he does. Maybe semiconductor. I don't know. But he wasn't an engineer. He was a businessman. And because he was kind of that, conductor of the orchestra, he didn't actually need to know everything. He just had to sit there as a leader and say, this is not what we're doing, this is what we're doing. And so to really answer your question, knowing engineering and knowing leadership skills, they don't always go hand in hand, but it can help. Yeah.
Going back to the airplane was the captains had a lot of pain. I think all of us and you especially have witnessed failure at some point during competitions. So what do you think is the best mindset to just calm down and then solve the problem?
Oh, perfect. Rain, what do I always say?
Yeah, hi.
Booyah, hypa, don't be afraid. I constantly remind people over and over again, don't be afraid. And when I'm playing video games with people, I remind them, you can't panic. When you're panic, your thinking capacity drops. So you have to kind of be encouraging, right?
I'm unfocused when you're panicking.
Yeah, you do get unfocused. But at the same time, right, let's say you do a match, they're panicked, they made a mistake, they didn't realize that hitting F1 rescans the USBs and now your joysticks work. Now that happened, they remember that. They're never going to make that same mistake again. So a lot of people, they make a mistake, oh, we're never putting them in again. Wrong answer. You want to put them in again because they're never going to make that mistake again. You got to drill it into them. And on 694, when people make simple, silly mistakes, we have this fun thing where if they cause the foul, we make them do push-ups. Sometimes they have to do a lot of push-ups. Sometimes they don't have to. How well do they read the rules? I don't know. So, yeah. There's a lot of things about human states of mind that can cause people to think differently about things.
And of course, everyone thinks differently.
Everyone thinks differently. So now I think I am going to release you because we're almost at the time. But a lot of these problems, right? A lot of people thought of them, and we thought of them here too. As a lot of engineering problems, but not all of them were actually engineering problems. Only the fountains of Bellagio is really an engineering problem. Ryanair Flight 301. If the pilots recognized that there was a conflict in the answer between those two pieces, they would never have taken off. They would never have gotten off the ground. If Houston Airport, thought of it as an engineering problem, they might still today be getting negative reviews, but spending all this money to do something else. So it's only when you start thinking of things not just as engineering problems, but how we use these systems, do we find a set of solutions that actually work. Yeah, you got to broaden your horizons. So, all right. Thank you, guys. If anyone has questions for me, you can see me after class.
It's a DJ, no man.
Does Typeform do any summer programs?
That was fascinating.
Yeah.
I've seen the quadrant.
Yeah, I tried to pick problems. I tried to pick one classic problem that was good. If you go into engineering, you're probably going to learn how to do one. But I also tried to pick problems that I really well know. But also, I wanted one real engineering problem and one psychological problem. Yeah. I don't want people to always think engineering. No, it's not right.
Was that actually laughing out loud?
Got a short disguise. Yeah. What's up? Oh my god, if you didn't have any problems, the amount of times that we would have better solutions, oh man. Humans are usually the problem. Mark my words. Humans are the problem sometimes. All right, Brandon.
All right.
Small bit.
Can we take a water?
Go for it.
This like thirsty?
Do I have a box now? I do. It's cool. Do I have one to give? No.
I know that guy. That's fine. Hold on. Why here's more food? That one open.
Maybe I'm 45.
I know.
What do I always tell you?
Hold on. Wait, we think. No.
We're like Daniel.
No, I usually
What? I seen you from the NYC
No,
first.
I don't get paid that much.
Yeah.
Oh, did I say that out loud? Yeah, I did.
So what you just thought.
No, but not that one.
Stay.
Wait, do you have
For Barrett?
But I actually don't want to stay.
He said he'd give me my
Some safety advice on
advice in engineering. What's that?
because I'm trying to, it's not kind of ridiculous, but for the past few years, I've been trying to design a spider.
Yeah,
I'm trying to press the button, so when it comes out, the PSI pointer is, it feels like it's gonna break still. So how do I exactly like
But actually,
prevent that from happening?
I'd have to steer the dial a little bit more. There's a lot of principles here that are.
You wanna, I'll put it about my notes.
so we all kind of like,
If I brought my notes,
I don't want the freedom.
you know what it's about?
It's 25 or 20.
who is this? What are you doing, bro?
I feel like I'm dealing drugs right now. What's up? Who's the next person in here, or is it lunch? I think.
The pressure. It's not exactly. Hopefully, I wrote it and then it's like something that like really wrong.
So your job.
Oh my God, we're still seeking to be the first. Hardest thing was basically a photo.
It's kind of hard to go. Yeah, you are going up the range and change to them. Oh, yeah. Don't have to go down those lines. Scrap. But those are really, it's pretty. I watched a YouTube video, the guy, he actually, he doesn't have one brother, and that's I don't want to be partial, I picked up on time. I just want to be able to use it. And I'm hearing this, so you're able to use this, like, you
Do not know.
Yeah. Wait, the movie. Oh yeah. No, not 95. Like 100. Yeah,
Let's say.
I think it's one of the biggest things wrong with it. I'm not sure, like, I'm within the same thing. I don't know. And like, first I was like,
That's like, yeah, so I know, right? Can't wait till.
Are not here?
They're not here yet. I've been in,
What?
you find them? Can you find them?
I go get here. Just need it. Yes. You
Just left. Bruh. Can you find Ivan? They're supposed to be in here. Oh yeah, I'll go. They're supposed to be in here. Hi. Do you guys want face camera? What is this? Stream into YouTube.
Oh, so I don't need my laptop.
Yeah. Well, I mean, if you're gonna run code and stuff like that, then not okay.
Oh, you're not gonna do a demo?
Yeah.
I mean, you wanna get me the limelight for admin?
And why are so many people here, Ivan? Why are so many people here? Okay, well, you sign in here.
No panic attack, you got this. It's better not to do classroom, not lecture hall, you know?
And then I'll set up a projection for you guys.
At least
You got this.
Okay, suspicious.
This is like, whose computer is this?
Brain.
This one carbon. Oh.
Wow, it's really taking a hit. Yeah.
What does it do?
What do you Oh wait, you have
Yeah. A lot of
I didn't do my homework either. This has been my entire night. You sleep? What time do you sleep?
I said it 1:30.
I almost like missed one. Like I almost get Why is it doing that?
Because I thought I was gonna get it for work.
There's too many people here.
But apparently, I don't know.
Like here, there's like 5 people. Yeah, I feel like 5 people. What they share the problem is that like why isn't it working? I can't get it to show up over here.
You drag it over. It's because it's extending. You have to drag it over.
But we still want to see it. Wait, we still want to be able to
Yeah. Oh, then just do a duplicate.
Okay, that makes sense.
Where's the
I don't know. All right. We are.
aspect ratios?
It's fine. It's fine. It's fine. It's fine. Okay. 1080.
Alright, super.
Whoa.
Yes.
It's just as
Now
bad.
there's not black bars in his screen.
Let me check OBS.
OBS.
All right, it works. You guys are fine.
Okay, cool.
All right. Let's start. So, welcome to our presentation, Beta Testing 2023. I'm Ivan. This is Vincent. And here we'll just be talking about, what we found throughout our process when we worked through the beta releases of WPI for 2023. So, we're going to go over, updating old projects to the 2023 season, the changes to the WPI library, and then new features are being introduced, namely, 3D geometry classes, network tables 4, and April tags. And, I made a couple tiny URLs if you just want to look through documentation, afterwards. You'll get these slides, I think. Maybe, yeah. Someone will probably send them to you.
No, that's their phone out. Sure.
Okay, now we're gonna go over how to update to 2023. So basically, there are 2 ways to update it. One way is you could just use the WPI lib import project tool. You get that by just clicking Control-Shift-P or Command-Shift-P if you're on a Mac, and you can just search for this WPI lib import a WPI lib 2020, 2021, or 2022 Gradle project, and then it'll automatically do everything for you once you set up all of your settings in there. And there's an alternative option where you can just change the Gradle, the build.gradle from your the Gradle Rio version from the previous whichever version it's on right now to the 2023 version. Right now it's currently in beta, so beta 6 right now, but it'll be released and you'd have to change the version to the released version. And then also you have to change the Gradle to a newer Gradle version. I think the newest currently it's Gradle 7.5.1, but I think 7.3.3 also works. And then also after doing that, you need to make sure to update the vendor depths. So there are really just 4 main vendor depths you need to update. CTRE, which is used for your motors like Talon your motor controllers, Talon FX, Talon SRX, Victor SPX, and also like the Canon Coder, Canon Fire, and Pigeon IMU, and then also RevLib, which is just the Rev render depths for Spark Max and the color sensor. Also the Kawaii Labs vendor depths, which is used for the Navex. And also there's a new vendor depths I think this year for Photon Vision, which is basically the library you'd have to use for April tags at this point. Okay, and then we'll go over some just new changes this year and also breaking changes from previous years. So right now, WPILib in 2020, I think, they updated to a new command-based format. And so you'd have to be able to like update the command base from the old command base, old commands to the new command base, which you would need the vendor depths to install. And we have just some examples. This is like our intake subsystem. Basically, it's just the important thing to note is that instead of extending subsystem, you have to extend subsystem base now, this subsystem base. And that's pretty much it. And also for commands, you have to extend command base instead of commands. And then after that, there are also changes to the button library. So important to note is that the button class has been basically replaced by the trigger, just for clarity. Also, the several like functions have been basically changed. The one active and one pressed from the previous button class is now on true in the trigger class. The while active once and while held is now while true. Toggle when active is now toggle on true. Cancel when active is just triggered rising, or just you can use command.until. And also, while active continuously, this has been removed, and you'd have to use either a run command, a repeat command, or a command, just do command dot repeatedly. And the dots are on the slide, which you'll be able to get later. And so yeah, this is like kind of our like kind of button bindings. As you can see, like the thing that the conveyor, which should be running continuously, it runs without while true. So basically, while the operator holds down the button, this command will continuously run. And on the other hand, the intake.extend, the way we do it is we just have like a kind of some like switch, right? And it'll just set like a integer or some value to like true, and then it'll just extend the intake. So this should only have to run once. So in this case, we use the onTrue from the trigger class. And yeah, there are also now new command-based HID classes. So previously there was just a previously there was just a like Xbox controller, PS4 controller, and a joystick controller. But now there are new command Xbox controllers, command PS4 controller, and command joystick controller. And these three just make it a lot easier to like bind like buttons to a command. So this is like basically what we're using here. The while true will now return like a trigger for the operator. After it returns trigger, and you just have to be called while true and enter in a new conveyor shoot command. And then now there are like new classes in the trigger framework. So there's an event loop, which basically continuously runs through like several actions. And there are three important methods. The bind method, which is used to just like add a new action into the like the thing that continuously runs. The clear, which removes like previously added bindings, and also pull, which just runs through the bindings. And so I'm pretty sure this is just the like interface, the lower level of it. But the Boolean event class is what uses event loop, and you can use .and or .or to be able to combine multiple like Boolean events together. And basically what it does is if it's true, or like if basically if it's true, it'll run some action that you give it. Yeah. And if high runs like that, sets the action to the signal. There are also drivetrain changes this year. So WPILib has changed differential drive and mechanism drive from the NWU coordinate system, which you can see, or to the wait, no, it changed from NED to NWU. NWU is the one to the right, and basically you see like the the axis of rotation has been inverted. So basically you just have to like set the z-axis, their axis of rotation. You just have to invert that, and once you invert the angle, it should work fine. And then the reset position for odometry and pose estimators of the drivetrain, they now take in wheel distances instead of wheel speeds. And also just the kilo drive class, which was like depreciated previously, it's now removed. And the holonomic drive controller, which is used in the ramz command, that's now it takes in continuous input on heading. But I think this is just like a WPI lib change, so there shouldn't be anything in like your own framework that you have to change. And yeah, so these are like the mechanism drive specific changes. So again, mechanism drive odometry and mechanism drive pose estimator, they now use wheel distances instead of wheel speeds. So there is a new class for it. It's called mechanism drive wheel positions. And basically it just takes in 4 parameters: the front left meters, the front right meters, the rear left meters, and the rear right meters. And these just represent the wheel position with the wheel distances that each wheel has been traveled. And yeah, there's also the like Java docs on here, which you'll get. And then also swerve drive odometry and swerve drive pose estimator, again, also use wheel distances instead of wheel speeds. And these both are, I think, they both take in a swerve module position array. And you see the swerve module position, which is just a class which contains a rotation 2D for like the angle at which the module is, and the distance meters, which is just how far that the module has traveled. And it'll just take an array, depending on how many swerve modules you have, it'll take in just all of the positions and angles of the swerve modules. And there are also some command changes. So there are several things that have been like renamed. With interrupt, from the command class has been renamed to until. The perpetually has been renamed to repeatedly, and also unless is a new decorator, which it allows the command to run even if the given condition is true. So yeah. Also ignoring disable, which allows the command to run even though the robot's disabled. The finally do, which it allows you to run another like action after the robot command has ended. Handle interrupt, also which is handles like an interrupt or anything that's like broken. I think just like handles any interrupts to the command. Also, perpetual command and dot perpetually have been depreciated, and now they've basically been changed to the repeat command and dot repeatedly. There are also changes to the 2D geometry classes. So the rotation 2D, which was basically just took in like an angle and allowed you to convert from degrees and radians. They now have 2 new factory methods. So basically you can now call it rotation 2D dot firm rotations, and you can give it some rotation value and it'll create a new rotation 2D. Or you can use rotation 2D dot firm radians, which takes in a radian value and it'll create a new rotation 2D for you. And yeah, you can see those 2 functions there. They're static, so you have to use rotation 2D dot. The translation 2D, it now has a get angle function. So it just returns the angle formed by the translation and the positive x-axis. Yeah. Okay, and then there are also like some miscellaneous changes. So the speed controller and speed controller group, which I think were updated to motor control and motor control group last year, they've been removed. The matrix utils class has been removed. And then they've also removed several deprecated functions from sim device. Although I think you don't really need sim device. And also the get instance functions from several classes have been removed, and they've all been converted into static functions. And also compressor.enable, is now deprecated and is replaced with .is enabled. Yeah, and I'll leave this slide up for a minute. Too much.
Okay, so moving on to new features. So let's start with the new 3D geometry classes. Here's 4. So WPILib has added new 3D geometry classes to support vision odometry. So we have pose 3Ds, rotation 3Ds, transform 3Ds, and translation 3Ds. So pose 3Ds visualize the position of objects in a 3D space. So essentially, if I have a tag, up on the wall and my robot's on the ground, it can track the X, Y, and Z coordinates relative to your robot, and that will be a pose 3D. It also contains a rotation 3D, which is just the pitch, yaw, and so I don't remember. Roll, sorry, of the thing you're tracking. And that's all relative to whatever is trying to detect your target. So pose 3Ds, they're stored as rotation 3Ds and translation 3Ds. That's essentially what I just explained. Yeah. So rotation 3Ds just represent, an angle on a 3D plane. They have roll, pitch, and yaw as the three dimensions. And then a translation 3D just represents a point in, 3D space. And transform 3Ds, they represent a transformation in 3D space. And they can be used to represent, a change in the pose 3D. And they're represented by matrix. But it can also be represented as a 3D vector, if you know what that might look like. So a couple other ones are twist 3D, which represents change in distance along a 3-dimensional arc. A quaternion, which is similar to matrices, but they make the calculations, between quaternions easier and less rounding error. Coordinate axes, they represent a coordinate system within the northwest or NWU coordinate system. And then coordinate system, it's just a helper class that converts pose 3D objects between all the different types of coordinate frames. They've also added a couple of pneumatic simulation classes. So we have solenoid simulation and double solenoid simulation. Essentially, they just represent a real solenoid in simulation. It's used to be able to do something else, like using the physics classes, but now they fully support all this. And then they also have the pneumatic control module sim classes, so the one from CTRE and also the one from Rev. Another one is computer vision util. It's essentially a utility class that takes the position of a 3D, like a pose of a target that you're tracking. So say retroreflective tape on a wall, and it combines it with your robot's odometry to essentially add another data source onto your odometry so that we can kind of reset the odometry to a more accurate state. Yeah. So next is network tables 4. So who here knows about network tables or have used it?
I've heard of it.
Okay. All right. So network tables is essentially just a way to distribute data throughout the robot. It's not limited to robot code. It's basically I'm putting values onto a local network, and those values can be accessed by all the devices connected to that network. So you could have tools such as Smart Dashboard, Shuffleboard, or Glass.
which are just visual dashboard ways that we can see them. They can also just be passed around throughout, your robot code. Say, I have, say I have a shooter subsystem, and I also have a coprocessor like a Limelight, which tracks vision targets. And so the Limelight, it would put data onto the network table, and now inside of your shooter subsystem, you can get values such as the distance from the robot to the target, and you can calculate, maybe you want to interpolate between RPM values and shoot like from anywhere on the field based on a couple of data points that you gathered earlier. So previously it was at generation 3. The way that it worked is essentially it was a dictionary. If we all know what a dictionary is, there's a table there. So essentially you have a key value and just the value associated with that key. You can think of it as like network tables. It was a couple of big dictionaries that just had names associated with them. So say it was, photon vision or shuffleboard or camera utils, stuff like that. Those would be entire tables. And then in those tables, you would have keys and values associated with them. And you can update them from anywhere. So this year they're releasing Network Tables 4, which is, a shift to a different model. Instead of having this dictionary system where, we just put values onto a dictionary and then every time we want to get a value, we just search through the entire dictionary, find the key, and then get the value associated with it. Now we have a publisher and subscriber model. Essentially, we have values which are published by publishers, and then those are read by subscribers. And subscribers basically listen onto topics, which are just data channels that are used to pass around all this data. And these topics, they can have properties called essentially metadata. They hold things like the data type they are, and you can also add things, custom properties such as, if you want to have a gear ratio passed around or a conversion factor, stuff like that. Yeah, and finally, I think in the definitions there's entry. So entries are basically just a combination of subscribers and publishers. So there are a couple types that are supported by network tables. As I said before, they're all represented by strings as like properties of the topic. They support floats, doubles, and strings, booleans, arrays, and just bytes, just random bytes, arrays of bytes. And this is pretty flexible. Like you can basically do anything with this set of types. For arrays, they still specify you still have to specify which type they all are. So like the other ones, just like float, double, int, string, boolean, bytes, they all apply to array. And so network tables essentially network tables, they use a client-server system where basically you have clients and then you have a server that manages all the interactions between all these clients. So clients would be, as I said before, coprocessors and maybe your robot code, or perhaps you might want to have additional other sensors on the robot. They don't directly have channels to talk to each other, which is why the server is there. It acts as like the communication hub between all the clients. So on publish, like the publisher will attach a timestamp value to the data when they publish it, and the server will keep track of the latency between each of the clients, and so they can so the clients know that, oh, this data is fresh, it's not like stale or old, and like you can also retrieve these timestamp values, which you can use to do comparisons or just to make sure that the data you're using right now is not like old, like, oh, maybe I'm like the data before was from like 5 seconds ago. Oh, the target's not even there anymore. Why am I trying to align to it? Yeah. And then, so topics, they can also have multiple publishers and subscribers. It's not just, so you can essentially publish to any topic you want. But like, yeah, but like you have to provide the name of that. So that topic. And then subscribers, they're multi-subscribers. Essentially, they take in multiple values, but since like there are multiple values, there's like special like other classes for them, like pollers, which just go through the list of information coming in. Generics. So there are also generic publishers, entries, subscribers, topics. Or not topics, but yeah. So essentially, they just take in all the data types. It doesn't matter which one you want, or like which one it's specific for, because they can take in any of them. Which just, I don't know. You might think of it as like bloat, like, oh, why am I having more of this thing when I know it's a double? Why don't I just have a double publisher? But I guess it's just a design question, like if you want to specify or not. And finally, you don't need to update. WPI Lib is supporting both Network Tables 3 and Network Tables 4. So previously, you would probably be using network table entries to like pass as like the thing that's being passed around, but they're not deprecated and they're still being used. So all your old code won't break. Oh, you do need to update a little bit of code though. So they've changed so you have to start the client, right, in your robot code. They've changed the method for that. You have to specify which client you want now. So you might want to start, so they have start client 3 and start client 4 now. So that's just a tiny thing you have to change. Yeah.
Yeah.
Where in your robot code do you specify that?
So our robot code, we actually have a library that kind of handles it for us. So when we like instantiate like stuff, so we call them smart numbers and smart booleans. They're essentially just a wrapper around their API, like the network tables API, and that kind of handles it for us. Yeah.
I think like normally you'd probably have like some kind of like I think it's like a network tables, like you just have to like create like some network tables on like robot container or something.
Okay, I just remembered. So automatically your robot code will start a server. I'm sorry, not a server, a client called Shuffleboard. So there are a couple default ones that are started. I think Smart Dashboard is one, Shuffleboard, I think FMS Info, and then another one. But yeah, so there are a couple clients.
Camera server.
Oh, and camera server, yeah. So those are the 4 that are default started. So what I'm talking about is like creating additional, so you know how I was talking about tables before? Yeah, so you can start more of these separated tables essentially, or network tables. And they're all on different networks, right? So they don't know what's going on within each other, but you can start more of them so that, if you want one specific for limelights or your vision system, you would create a new client called, Limelight or Vision System. Yeah. Does that make sense?
Yeah, thank you.
So next is, I think, the most interesting thing, April tags. Essentially, they're just visual tracking markers. They have a fancy term for that, which is like fiducial or something. But yeah, essentially they're just artificial markers. Well, I have a couple. So they're like very different from the surrounding area, right? So that's what you're gonna track. Like previously, I guess with CV, you can put them down. I guess if I wanted to track a couple points, just in this room, maybe I would want to track the top of the smartboard, or the edge of this podium, or the clock. But what if I have multiple clocks? Like, then how do I know which clock I'm looking at? And then I guess your localization gets confused, like, oh, which one am I looking at? With April tags, each tag is different, at least in a family. And yeah, so if you just look at them, they're like a 4x4 grid, right? Essentially, all of them are just different in a family. I think in the family that FRC is going to be using, 16H5, it has 30,000 possible tags, I think, something like that. But yeah, so each tag on the field will be different, or I'm assuming they will be different. Maybe they might have groups of the same tag. I don't know. But yeah. So they'll all be different. And so WPILib, they implemented something called, or I think I'm going to talk about this later. Yeah. So April tag field layout, essentially what they're going to give you is basically a JSON file of the absolute position of each April tag they're going to be putting on the field next year, in that JSON file. And then you can just go through that file and then identify, what their position is. And then, you're looking at the April tag, the relative position of the robot to that April tag, and you also know the absolute position of that April tag. So you can just sort of calculate exactly where on the field you are. And this works with like even just one tag. There might be a little bit of error, like maybe 5 degrees of rotation error, which might throw off the calculation, but it's like accurate enough if you combine it with all your other data sources like encoders and gyroscopes, like if you use a Navex on your robot. So what they're introducing is the 16H5 family, and they'll be 6 inches in width. So these are exactly 6 inches, so you can expect them to be this large. They're not ridiculously huge. So April tags are known for being able to be detected at like both really small and really large like scales, but you need high enough camera resolution to read them. Yeah. And so you can either write custom code off of the April tag repository by April Robotics, or you can use pre-built solutions like Photon Vision and maybe Limelight. Like Limelight, they haven't said anything about releasing April tag support yet, but I think they're hinting at it, but I don't know. Yeah, but it should make sense for them to do that, I think. So in FRC, there are a couple applications. You have 2D detection, so you can align to targets. Essentially, like when you track the April tag, you know where they are on the image, and then you can do a little bit of math and figure out where that is, relative to you, or just the angle offset. And then I guess you can center the tag if you're shooting at, say, a hub this year. Like maybe if they replaced all the reflective tape with April tags, then you just aim at the hub. and I guess they can also be used as targets to go to at autonomous routines. So like, say you're autonomous, like, I don't know, next year maybe you have a pick and place game. You track where the entrance to, I don't know, maybe they're stacking boxes. So you can grab boxes from some spot on the wall and you can travel to there. As for 3D detection, you can perform, what I was describing, absolute localization of the robot on the field. And as you see in the images, that's how they look like as they're being detected. The 3D is not perfect, but it's good enough for, I think, general application. There's a couple parameters that you can adjust to tune the detection of the tags. There's decimation, which is basically just downsampling the original image that you're getting, so that the processing will be faster because you have less pixels to process. But this also decreases the detection range because, like, say I have a tag that's 20 feet away. It's not going to be really big, right? So if you have 1 pixel to that tag, then it's not going to see it. There's also blur. I normally wouldn't mess with this unless noise is a really large issue with like the data that you're getting. So noisy data, that could probably be from low light situations and the camera's just not really meant to handle that. Yeah, that's the only, or just the camera's really bad and there's a ton of noise. It applies a Gaussian blur. You kind of don't need to know what that is. Basically, it just smooths out the image. Yeah, I would, if you do add blur, it's just a tiny amount. Like, if you go all the way, it's just a mess. You won't be able to see anything. And then finally, threads. It's just the number of parallel threads that are used to process, like run the algorithm to process the images and get the pose data. So I can really quickly run through how they detect the tags. So we start with the original image. That's just, raw data from your camera, RGB, brightness. And then we remove all those colors. So we're only left with brightness. So it becomes a grayscale image. Now we decimate the image. My image is really small, so like there's probably no visual difference, but I'll tell you it's there. So essentially it just reduced the amount of pixels that it has to process. You can probably observe tiny bits of pixelation, but it's not really apparent in that image. But if it blows up, then like you can see it. And then adaptive threshold, that's essentially just assigning each pixel one of 3 values. It's dark, it's light, or it's, I'm unsure. Maybe it's like slightly gray or something. And then it just creates blocks of that on your image. And then segmentation is next. Essentially, that just groups the blobs that are connected to each other. And then it also like removes the really small specks because you wouldn't expect a really small speck of just a color to be a tag. And so it kind of groups everything together into like little, like they're all assigned different colors. And so you can tell like the corners of things. And then next is quad detection. Basically, it just tries to fit a quadrilateral onto all the segments, and then tries to fit like a quadrilateral on all the segments, and then it just, if there are other smaller quadrilaterals in a larger one, then you can assume it's like a tag, and then we start decoding what the tag is. So each one has a different ID. And basically, they have a database, or I guess you can't call it a database, but a dictionary of just matrices of the 4x4s, and they just take out like what what they're getting from the image. So like 0, 1, 0, 1, 1, 1, 0, 1, stuff like that. And then they compare it to the entire dictionary to find the one, like the ID that they're looking for. And if they can find it, then they just, show it. And then the final one is to just fit everything back onto the original image. There's a little bit of computer vision trickery that goes into that but essentially you have the corner coordinates on your decimated image. You essentially just approximate the new corners on the original image, and then it just shows that. It just exports that. And you get pose data from that, pose 3Ds. So you might run into a couple issues when playing with the April tags. One is motion blur. I think that's the biggest problem you might face. Low FPS is probably next, and then low detection range is probably the final one. I mean, I guess it depends on what your application is. That'll change like what is more of an issue for you. But motion blur essentially, so the assumption that the detection algorithm makes is that your tag is a square, or at least a quadrilateral. So if it's not a quadrilateral, so if you say, like, if you know what motion blur looks like, it'll just be like a really long rectangle, or it could have edges that like just doesn't look like anything. It might just be like the background or something. So yeah, that might be an issue that you run into. We were testing yesterday, and essentially that's our problem. Like, motion blur just makes it so that we can't detect the targets while the robot is moving. So it thinks it doesn't see another tag, right? And so it just does weird things to try to find it again, but it just makes the problem worse because it's moving faster and faster. So when aligning to these April tags, you might want to slow down the robot, maybe load gear if that's what you use. And another way to, minimize these this motion blur issue is using a global shutter camera. Basically, cameras work, or most cameras work rolling shutter. Essentially, they just go through all the pixels one at a time to capture information. That's bad because if you move while it's doing that, then each pixel will have a slightly different time that it's being captured. But global shutter cameras just take the entire array, matrix of pixels, and it just like dumps that data. So you know that all the data is from one time. So it would minimize this motion blur issue, or at least it would help a little. Low FPS. So the algorithm is a little processing intensive, or I guess a little is an understatement. It's kind of processing intensive. Currently with a Raspberry Pi, I think we're averaging 10 FPS at 960 by 720, which is pretty bad because the detection range is 16 feet right now. Yeah. So you would probably want to bump, yeah.
What Raspberry Pi is that, by the way? Just for reference.
In the so we flashed a Limelight with photon vision, and that uses a Compute Module 3 plus, I think. Yeah.
So do you think that'd be better than a Module 4? Like,
it might be. So there's a little bit, there are numbers that photon vision put out. Sorry. Oh no, to be honest, I wouldn't expect it to be much higher, maybe like 20%. Yeah. So okay. So right now, this is what we're using. So this cell, this row. So they're getting 15 FPS, which is, I don't know. We're not getting that. But But yeah, so they're getting 15 FPS, and with Raspberry Pi 4, they're getting 17. So like just negligible, I guess. It's an improvement, but it's not the best. Yeah. How much? 14. Okay. So low detection range, that's essentially just, I guess bump it to higher resolutions, but then that also decreases your FPS, which, you just find a balance between those. And then running detection code. So you can run it on the RoboRio. That has less latency, but it has more overhead. So you might run into loop overruns because you're stealing processing power from like an already weak computer. If you've looked at the RoboRio specs, they're kind of bad. They're really bad. But yeah, that's the RoboRio. But on an external processor like a Raspberry Pi or a Jetson, or someone even suggested small computers like the B-Link. Those would have higher latency, so because they have to go like pass the data through the network through network tables. They generally do have higher performance because you're offloading all your processing like capabilities to this thing, and it's only doing that thing. So it would have more processing power. It depends on what device you use also. Like the computer, I would expect to have like, I guess, either the highest or the mid, but the Jetson, it's kind of designed for, computer vision purposes, but it's also hard to use. I've been playing around with it for about a week, and I don't know. It's kind of, I can't get it to work properly. Yeah. Okay. All right.
Okay. So currently, there's really only like one big library that supports April tags, which is PhotoVision. And yeah, so there are several like just important functions that PhotoVision has that makes it just really easy to be able to like align to April tags and stuff like that. So Photon Vision, it has just these 5 functions, which we use to be able to align to a target. So it has get latest result, which just basically returns the latest like object that the latest like frame that the camera is like found, and then the get best target just gives us like the best like object that it detects. So if we have like multiple like April tags, it'll be able to give us like the best whichever one it sees the best, and then whichever one it sees the best, it'll be able to align to that one. So we also have these three functions: calculate distance to target meters, which is under the Photon Utils class, and it basically just it basically calculates it has an algorithm which can calculate the distance from your robot to like the target, and get yaw, which just tells us how far the angle like just how far off our robot, like the angle of our robot is from the April tag. And we also have the estimate field to robot. So this is something that you can use with odometry to be able to pretty much just to be able to much, I guess, like more accurately detect where the robot is on the field. Because you'll have like 2 different streams of data, one from the odometry of the robot and another one now from the camera. When it does detect the April tag, it'll tell you it'll tell you where the robot is relative to that target. So we have some example code here. So this is what we were using to test on one of our robots. So basically we have these 3 main functions here: the has target, get distance, and get angle. So the has target would just return if the camera sees any target, and it just uses the camera.get latest results and .has targets function from the Photon Vision library. We also have the get distance. So the get distance uses the Photon Utils.calculate distance to meters function, and it takes in 4 parameters. It takes in the height of how high your camera is. It'll take in how high your April tag is, which during the season you'll be able to like determine from the JSON file they give you, and also the pitch. So the pitch is just how the angle of the camera. So yeah, and then also the pitch of the target, which you can use the result that get best target get pitch to determine just the angle of the April tag, and also get angle, which just uses the result that get best target that get ya. And yeah, those are like just the two functions we use to be able to align, and we'll just call it continuously in our drive train align command, and it aligns pretty well, but we do recommend like some kind of smoothing algorithm. Like we use we were using like a low pass filter, and then also like that combined with like just PID, and just because we want to limit like how rocky the robot gets, and just because of like again the motion blur of like the camera, it kind of does some like weird stuff with like it just starts randomly moving really fast backwards and something like that, just because they can't really see that target very well. So yeah. Okay. And yeah, there's some like references for the April tags. So like, yeah, there's just like
Research
papers based on April tags, which you can look into. If you were like also just like writing like your own algorithm or something like that.
I do not recommend rewriting the algorithm.
Yeah, I think Photon Vision's algorithm works just fine. Yeah. Okay. I guess.
Question.
Yeah.
Yeah.
How would the processing for the algorithm work for 3D basically when it comes to table tags?
Oh, okay. So we know the corner coordinates of each tag, right? They can determine, so once you have the coordinates, you can basically draw the quadrilateral. And with that distortion, because they know that it's 6 inches across and also a square, you can use math to calculate, based on the distortion, like what the angle or the rotation that it is, essentially, you've gotten.
Yeah.
Before you mentioned the network tables, what kind of applications are there for like the computer interfacing with the robot? Like what kind of information could you send back?
Yeah. So like, basically like on our robot we have like sensors like the IR sensor and the color sensor, right? And just to be able to like get the values of like these what the color sensor produces and like just stuff like that, you need the network tables to just like be able to like get that data from like the RoboRio to like your computer. And then like for we also have like we're also able to just send values from like our computer to like the RoboRio. So like basically if you want to like change the speed of like your shooter on the fly, like if you're tuning something, like tuning how fast your shooters to go, we have like basically a smart number, and it's basically like how fast the RPM of the shooter, and pretty much you can send like that kind of value to like the robot code just through that network. So yeah, I guess just for like tuning your robot, and also just like being able to access sensors and like sending values between the robot.
Yeah, you can also define like states in your robot. Like if you went to the state or the presentation on states, or like state control in a robot, that's essentially what you can return to the human, because we're driving, right? And we kind of need to know like the state of the robot, maybe what it's doing or what it's detecting. And that is what we use the data for. Also the tuning, and also just a couple other toggles that we can manually trigger on the computer.
Also, how do you interact with that on the computer? Is the smart dashboard?
Yeah, so we use like an application they provide called Shuffleboard, and like on Shuffleboard it'll give you basically a list of like all different like values that are on like the network, and by just adding these values onto like their like kind of the screen or something, or
Yeah.
the like UI, then you can basically like set values and also like toggle, like there's like different kinds of like, I guess,
Like widgets.
widgets, yeah, different kinds of widgets.
Representations of the values. So like if it's a stream of data, you can have a graph, or if it's like the position of the drive of your robot, then you can have a field and you can see like a virtual robot driving on it. Some teams have also written their own application to like interface with the network tables, and maybe they just prefer like that way. Like they think it's cleaner, it's more reliable, stuff like that.
Yeah.
Any other questions about this or like anything? Burning questions. All right.
Okay, well, thank you for coming to our lecture. I know we like kind of went through like the breaking changes and stuff pretty fast, but we just wanted to get to like the April tags, which we thought were like the most important, I guess, like the biggest change in like WPI lib. But
Yeah. So they're not like completely removing retroreflective targets like this year. They're going to support both retroreflective targets and April tags. I don't know how they're going to do that. Maybe they'll have April tags in the targets, but whatever. But they're planning on transitioning to April tags like solely, just because I guess it's more accurate. I guess it's more convenient, more accessible. Like you can just print it out on a printer. So yeah.
And also, I guess like biggest thing of April tag is just like being able to differentiate between like different positions. So using April tag, they'll be able to provide like more I guess places to align, and more like places where you can like use the like pose estimation of the camera, and just to be able to get more accurate data.
Yeah, like with retroreflective targets, it used to be like really crude. You'd have to like look at the shape of whatever you're detecting and like guess which target you're looking at. But now you know like a definite, difference between all of them.
Okay. Yeah, but everything's going to be posted on like either email or something like that.
Maybe.
But there are like there's documentation on WPI. They have like just like some guides to like just different things. There's also like the Java docs, which some of it we have posted there. Which if you have any like problems with it, then check the docs. All right. Thank you.
Thank you.
Thank you for the presentation. No problem. Yeah, I went pretty fast, but like honestly, yeah. Wait, you might know. So this doesn't sound like
What do you describe your
General understanding.
Okay.
I can those.
We'll make sure to make how did you like email how we'll send email. Yeah, I know, but we have
They said that they
I would have been fine without. Now that I heard it.
Well, I hope. But, I mean, I guess I can write down an email if you want. I'll just write on the slide. What's your email?
power. And so ads and advice team that
Alright, thank you.
yeah. No, just one personal way to get the values for us. Also,
I mean, like, it can like help you like if you do like in the future, if you even like mentoring different teams on like story graph stuff like that. But like, yeah, I mean, if you have like any trouble, like you can always like email us or like we also have our GitHub. Like if you have any issues, like you can always like contact us. But I think
I can fire up like an example project.
Yeah.
My team's actually been doing surgeons, the start surgeons.
Oh, yeah, that's cool.
We said a lot of back here the shoots and get thing to work. I don't know if that's what I'm still on.
I think we'll be kicked out in about a minute. But so if you look at how our acting on this. So, oh, it's lunch, right?
It's lunch now.
Right. So,
How was it?
so we have Martin, right? This is something from our library, but we can look at like how this works. Platinum did.